Hi, in this video, let's continue our discussion on a pair of lines cut by a transversal. In the last video, remember we talked about a pair of lines cut by a transversal and certain pairs of angles are called corresponding angles. So today we'll discuss certain pairs of angles that are called alternate interior angles and alternate exterior angles. So here's a pair of lines. These are any old lines. They need not be parallel. And the red line is the line cutting both of the blue lines. And this red line is called a transversal. 4 angles are formed here. 4 more angles are formed here. Let's look at angle 4 and angle 6. These two angles. What do we notice about them? Notice that this transversal, which is a line that extends infinitely in both directions, by one of our assumptions about the Euclidean plane, separates the plane into 2 parts. Notice angle 4 lies on one side, angle 6 lies on the other side. That's why they're called alternate angles. They're called alternate interior angles because if you notice, these 2 parallel lines form the space in between them and this 4 and 6 lie in that space. So 4 and 6 are called alternate interior angles. Another pair of alternate interior angles are 3 and 5. Alternate because 3 lies on this side of the transversal, 5 lines on this side of the transversal. Interior because 3 and 5 lie in the space between these lines. So one pair of alternate interior angles are 4 and 6. The other pair is 3 and 5. You have probably guessed what alternate exterior angles mean. 1 and 7 are alternate exterior angles. Alternate because 1 lies on this side of the red transversal, 7 lies on the opposite side of the red transversal. Exterior angles because if you look at the space that does not lie in between these pair of lines, if you think of that space as exterior, then 1 and 7 lie in that exterior space. So 1 and 7 are called alternate exterior angles. Similarly, another pair of alternate exterior angles are 2 and 8. Now, if you were to do an exploratory exercise where you simply draw any 2 blue lines, which are not necessarily parallel and a transversal, you'll notice 4 and 6 need not be equal and the same about each of these pairs. But when these blue lines are parallel, something interesting happens. And let's talk about that now. So let's look at this picture. I have 2 parallel lines, unlike the other picture, and a transversal cutting the parallel lines. So this line is L, this line is M. We suppose L is parallel to M. You've probably already guessed that each pair of alternate angles are equal in measure. So 4 and 6 are equal in measure. 3 and 5 are equal in measure. Same is actually true also about alternate exterior angles. So 1 and 7 are equal in measure. 2 and 8 are equal in measure only because these 2 lines are parallel. Now let's confirm that using transparencies. So let's recall the 3 basic isometries of the plane, which are translation along a vector, reflection across a line, and rotation about a point by a certain degrees. So I think to myself, I would like to prove angle 4 and angle 6 are equal in measure. Said another way, I would like to show that angle 4 and angle 6 are congruent. So which of those isometries is going to help me now? And think about it for a minute and you'll come to this conclusion that it's actually a rotation. Let me show you how we can convince ourselves 4 and 6 are congruent. So look at this segment and mark off a midpoint. I'm just eyeballing it, mark out that point. And now this is what I'm going to do. I'm going to copy the picture as closely as I can. There. And now I'm going to perform a rotation about this point by 180 degrees. And let's see what happens to this angle 6. Notice angle 6 was mapped to angle 4 by the rotation. So those two angles are congruent, they're equal in measure. So in other words, we're applying the fact that rotation preserves degrees of angles. So now you believe this equality is true. That same activity, if you paid attention, also mapped angle 3 to angle 5. In other words, when I performed a rotation about this point by 180 degrees, that transformation moved every point except that black point, and it mapped angle 6 to angle 4, angle 3 to angle 5, angle 1 to angle 7, and angle 2 to angle 8. So that gives us all of these equalities. So this is the theorem that we proved informally using the transparencies. When a pair of parallel lines are cut by a transversal, the alternate interior angles are equal in measure. So by saying the alternate interior angles, what I mean is the two angles that form a pair of alternate interior angles. Those are the ones that are equal in measure. Often we leave out this word in measure, and so keep that in mind. And also we can replace this alternate interior by the word alternate exterior, and the theorem would still be true. The converse of this theorem is also true, so let me briefly discuss that now. Let's look at what I have here now. Same picture, but I don't tell you that L and M are parallel. Instead, let's assume one of these equalities is true. Let's assume this pair of alternate angles 4 and 6 are equal in measure. So that same activity should convince you of this theorem. When alternate interior angles are equal, then the pair of lines cut by a transversal are parallel. Because if you rotate about this black point, which is the midpoint of this segment, and if you perform a rotation by 180 degrees, the fact that angle 4 and angle 6 are equal in measure tells you that angle 6 will be mapped to angle 4. Well, where does line M get mapped to? Notice M does not contain the point of rotation. We've discussed a theorem that says in that case, that rotation maps M to a line that is parallel to M. So that rotation maps M to L, and by that theorem we can conclude now that L is parallel to M. Now this converse is also true when you replace the word interior with exterior. So keep these new theorems and their converses in mind, and also more importantly how we use the basic isometry of rotation about this point by 180 degrees to convince ourselves that the theorems were true. Thank you.